Okay, so before we jump in, let's just walk through the exact scenario that we're working with one more time. So the idea here is that we have an unlabeled data set. This is just the general assumption. The assumption of this particular differential privacy framework. There are other differential privacy frameworks out there, but the assumption for this one is that we have an unlabeled data set. And one plausible example where this exists is we represent a hospital, right? And that hospital generates data. Inside of our hospital, we're collecting patient scans of a variety of conditions, right? But this data isn't necessarily labeled. No individual person has gone through and said, does this particular scan have, some particular phenomena? Are these scans of males or females, or is there a specific kind of tumor or a specific kind of other condition that is present in XYZ scan? Some of them may have that, but some of them may not. For now, we're going to assume that they don't. They're just images of people. What we want to be able to do as a hospital is to have a machine learning model that can make predictions on this set of images. So we're going to say these images are, say, radiology scans. Okay, so they're MRIs or CT scans or maybe an X-ray of a human body, right? So it's just the X-ray of a human body, and we as a hospital care about identifying certain things in that X-ray. We're going to say there are 10 things that we're interested in identifying. However, our X-rays, our images, aren't labeled, so we can't train a machine learning model with our data set. Our data set just isn't good enough. We have the inputs, but we don't have the outputs. And it's a bummer, right? So it's a bummer because we want to be able to have a machine learning model. We want to be able to serve our patients with the ability to automatically predict these things as opposed to having to have, doctors sort of see every image. And so we say, what do we do? Well, it turns out we know 10 other hospitals that do have this kind of annotated data. However, they don't want to give it to us. Maybe it's they legally are not able to, or there's a competitive dynamic. They don't actually just give us the data, but they're willing to let us sort of try something a bit more creative, which is this particular framework. And the idea is we want to somehow annotate our unlabeled data using their labeled data. Right? So what we're going to do is we're going to go to 10 different hospitals, and we're going to somehow pull out statistical signal from their data sets to annotate our data sets so that we can train our own machine learning model. Does that make sense? Okay, and the way that we're going to do this is first, we have each one of these partner hospitals train a model on their own data sets, right? So all 10 hospitals train a model, some sort of machine learning classifier. Doesn't even matter what the classifier is, whatever classifier they want to be able to using, or whatever favorite one is. Maybe it's an SVM or a deep neural net or something. Doesn't matter, right? And then we take their model and we predict it on our data. Okay, so we take their model and we predict it on our data set, the one that is sort of public to us, the one that we're allowed to look at. And that generates 10 predictions for each of our images, right? And why 10? Because there were 10 hospitals that we partnered with that trained 10 different models, and we took all 10 of them and we predicted them on each image, generating 10 labels. And now, where the differential privacy piece comes in is we want to take their 10 labels and generate sort of whichever label that they most agree on. So like we want to say, all right, there's 10 models, they're voting, right? Which label is the most likely given that, here are the votes. So maybe if all 10 models said, there's phenomenon number 1 in this image, right? Well, then we would say, okay, then phenomenon 1 must be what it is. But if half of them said, it's phenomenon number 3, but another half said it's phenomenon number 5, then we would say, 50-50 chance. It could be one of these things, could be the other thing, right? And so this is exactly what we want to do, right? We want to work with these 10 different hospitals. They're going to train their sort of each model in their data sets. We're going to bring those models to our data set. We're going to predict them over our data set, and then we want to calculate the argmax over their predictions on our data to figure out what the labels on our data should be so that we can train our deep learning classifier. Cool? So the first training round where like a bunch of hospitals train a bunch of models, that's just normal machine learning, normal deep learning. So for the moment, we're going to skip that part, right? And what I'm going to do instead is we're just going to synthesize some fake versions of predictions that they could have given us on our data set. So we're assuming that those parts already happened because I want to jump straight into the differential privacy piece because that's the point of this lesson. Okay, so the first thing we're going to do is import numpy as in p. I'm going to say num teachers equals 10. So we're working with 10 hospitals. Num examples, so this is the size of our data set. Num labels, the number of labels for our classifier. And we're assuming these are mutually exclusive at the moment. Like, it doesn't have to be this way, but for the sake of argument, we're just saying, you know, it can be one of 10 things, but it can't be multiples. You have to choose. But you could do this with, you know, 2 labels, 100 labels. You know, you could do it with multiple sets of 2 labels. This is very generic. We're just picking 10 sort of out of thin air. Okay. Now, we are going to synthetically generate a tensor where the number of rows is the number of teachers. Okay. So we have 10 lists of numbers, each coming from one of our teachers, and there's 10,000 examples from each teacher, right? And why are the 10,000? Because we took their classifier and we predicted each teacher's classifier on every example that we have on our data set. Cool. And now just a little bit of NumPy stuff here, and voila, we have our synthetic data sets. So fake labels, fake predictions. Okay, so these are all the predictions from one teacher, right? So there's 10,000 of them. And these are all of the examples for, say, the first image, right? So this came from the first teacher, this came from the second teacher, this came from the third teacher. So the first teacher thought it was label 4, the second teacher thought it was label 2, the third teacher thought it was label 9, et cetera, et cetera. Okay, and so now what we care about, what we're trying to do, is we're trying to, in a differentially private way, combine these labels into a single label. And the reason that we want to do this is based on one core assumption. And that core assumption is that these 10 partner hospitals have different patients. We're assuming they don't have overlapping patients, maybe from different parts of the world. Maybe we just sort of asked them and or proved that they didn't have overlapping patients. And this gets back to our core philosophy of differential privacy, which is saying whenever we perform a query, that query, you know, in theory is hypothetically perfectly differentially private if the output of the query does not change no matter what person I remove from the query. However, in this particular case, these don't represent individual people. These represent whole collections of people, right? So this prediction represents, right, and it has information transferring to it from a whole hospital worth of patients. This has another whole hospital worth of patients. This has a whole nother hospital worth of patients. So when we say combine this into one label, the perfect way for us to do this would be if, you know, the output of however we combine these labels, in which case we probably want to take the whichever one is most frequent, we get the same prediction, right? We get the same target, the same output of our query, regardless of whether or not we remove one of these hospitals. Because then, if that's our definition, right, of robustness, we would also know that we could remove any one of the patients from those hospitals and the output of the query would be the same, because it's you know, one patient is strictly a subset of the whole hospital. If that doesn't totally make sense to you yet, it's okay. We'll walk through this step by step, and hopefully it'll make more sense as we go along. So for now, all we want to do is take each image and convert, you know, this vector of predictions from all the different hospitals into a single prediction. And the way we're going to make that conversion is we're going to just figure out, you know, which one did all of them agree on. We're going to take what's called an argmax. Okay, so the first thing we need to do, so this is an image. So there's one image worth of predictions, okay? And we're going to compute some label counts. So NumPy has this nice thing called bind count. And what it does, it just goes through and counts the number of times it sees a certain integer. So it looks like 0, 1, 2 was the most frequent number. So if I look at an image, 1, 2, 3. So yeah, 2 happened 3 times. See how it counted? And so when we look at this, we see the most frequent one is 3. So I could, let's see, label counts. So I could go numpy.argmax, and it would say 2. Well, index 2, right? So which is the third one from the left. So this is the most frequent label. This is the one that all the hospital models agreed on, right? So all the hospitals predicted on our data set on this image, and this was the most popular answer, right, that these hospital models came back with. However, this is not necessarily differentially private. This is the exact answer from these hospitals. However, we have an interesting technique, you know, adding random noise to enforce a certain level of differential privacy. And so for that, we're going to turn back to our Laplacian mechanism. So we're review this a bit. So we'll say epsilon, let's set it to 0.1 for now. Beta equals 1 divided by epsilon. And so we're going to say for I in range len label counts. So for each label, add some flash and noise. And now we have a new set of label counts, right? So we actually took the counts and we're adding noise to the counts. Okay, does that make sense? So the counts is basically our mini database, right? So if you remember from before, like we have a mini database across these hospitals of label counts, and we're going to add noise to each one of these counts, and then we're going to perform argmax. And now, as you can see, the noise actually made us get the wrong answer. But this is something that we just have to be okay with, right? So this is going to happen sometimes, and our assumption is that later on, when our deep neural net is training, that it's going to sort of filter through some of this noise, look for all the ways that these agreed, and it will learn how to predict reasonably accurately. Okay, so this is new label. Okay, but this is not enough, right? So this is just one image. So what we actually need to do is iterate through all of our images. Let's go ahead and transpose this. So just so we can iterate through the rows. For an image in preds, new labels equals list. Iterate through the whole thing. That was so fast. So we have 10,000 new labels. So we have now generated a synthetic data set of new labels based on the predictions from all of our partner hospitals. And now you might be wondering, how much information did we leak? So a super naive interpretation of this could be just to add up all these epsilons, but we wouldn't just have to add up these epsilons, we'd also have to add them up for every time that we used them, right? So for every label count. So this would be something on the order of 100,000 times 0.1, like could be massive, right? And that's not what we want. The real innovative thing of Pate, which we'll go over in the next section, actually has a better derivation for how epsilon is being spent in this model. And it's very, very interesting, quite fascinating. And so in the next section, I'll show you sort of what this fancy kind of Pate framework is about, and how we can actually get a better bound than this current epsilon. But for now, if we were the hospital, right, and we had obtained these predictions, obtained these labels, and generated these new labels for our data set, I would then go and train a deep learning model using sort of all of my X-ray images with these new synthesized labels. And I would know that I have spent that my new model fits underneath a certain epsilon budget, right? That the model, the entire model itself, being a compression and a collection of all the epsilons from this data set, would be under a certain budget. And in the next video, we will actually learn just how low that budget can be. See you then.